Greetings to all. This is Professor Raja Subramanian explaining in this new video on a good topic called as practical implementation of deep learning. But it's not same like the videos which we have seen in normal sites or any other web pages, like implementation of different models for each of the algorithms or applications in which we actually leverage on. This is something different for those who actually learn deep learning in practical and those who pursue research in deep learning and especially in image processing. In this particular video, I'm going to give you a practical implementation of deep learning using some templated code which can implement the deep learning ImageNet models like VGGNet, ResNet 50, MobileNet, InceptionNet, custom models with CNN layers, custom model with dropouts, custom model with augmentation layers, and many other customized deep learning model aiming towards accuracy of the application in question. In this particular video, I want to make it very clear that this particular practical implementation can be very much useful for those who are very well interested in deep learning but have less knowledge in programming but have some proficiency in Python programming at understanding level. Now let us go into the application and let me go through the code to make you clearly understand like how you can pursue this particular code for your own research or practical applications or laboratory experiments. Yes. Now, the application what I take into consideration is to do classification on breast cancer images. And I am going to apply some ImageNet model, say VGGNet, ResNet 50, MobileNet, InceptionNet, as I said before, and then some customized CNN models apart from the pre-trained ImageNet models. And for this, let me take a data set into consideration, and that's I'm taking a data set called this breakfast 400x. And this data set is a standardized data set which is open source for research and has many images, more than 4,000 plus data is actually present for breast cancer images. And it consists of only two labels, say malignant and benign. And any images should be classified into two, so malignant or benign. And inside, if you go, you'll be having some set of scanned images, and those the breast cancer images is in the format of PNG. And I ensure that all the data are in the same format, say .png. And with this information, I go into my code and take my packages for deep learning. Yes. And now I go into the packages, and these are the packages which is actually necessary for my code. And those are OpenCV Python, which is actually Open Computer Vision package to use image inside my Python programming. Then I use TensorFlow package. And this TensorFlow, as I said in my previous videos, is a suitable algorithm, suitable package for using deep learning in practical. And I use pip for making the packages updated to the latest version. I install all this and come into my program. I have run and kept the code so that the time can be saved when I explain the code. Now I import the packages which are being downloaded. I'm importing TensorFlow. I'm importing Keras. I'm importing layers and models from Keras. So Keras has many layers, say dense layer, dropout layer, convolution layer, pooling layer, and so on. And many models also say VGGNet, ResNet, MobileNet, and so on. So it has everything, and I need Keras to implement my Python programming for using deep learning, and I directly import keras from TensorFlow. Then I go with matplotlib lib.pyplot for data visualization, CV2 from OpenCV, OS for taking the data out from drive, PIL, pillow package for taking the images and doing addition in the images, NumPy for numerical Python calculations, and pathlib for setting the drive for, and globe for identifying the particular object inside my Google Drive. Now I mount my Google Drive. This is what the most important code, and you have to be careful here. Like I use the word called as I'm going to use a templated code for deep learning implementation, in this video. So the word templated means that you need not change any single line of code except some small variations for your own research or practical application. And that is what the important thing in this particular cell of code where I'm going to mount the drive. Once you mount, you have to mount to the same Google ID in which you actually have your drive contents. And I have all my drive contents in my Gmail ID. The same Gmail ID I'm having my collab so that I can connect to my Google Drive from Google Colab. And this is what the path in which I have my data set in the Google Drive. And this is the only change what you have to make in your code. Say for example, in the My Drive of Google, if you have your data set in some particular folder inside train or test, you have to change that path alone here. Then I go here, I actually want to extract all the data inside that particular folder. And I know that all the data inside my folder are in PNG format. So I say to my program that extract all the files inside that folder that ends with PNG. So I take all the file names and I actually take that into consideration for image count. So I totally take everything and my image count will give me the number of images present inside. Then I actually separate them into two classes. One is a benign class and the other is a malignant class. And this I do by taking those into separate folders. As I said already in my train data set itself, they are actually in separate folders. So all the images taken from malignant will be inside a malignant dictionary and all the images inside benign will be inside the dictionary named benign. So that is what I made here. Then I just print my dictionary and see, and I could see like all my images are being read and over 4096 images are being read in this particular drive. So a pure quality research, like more than 4000 images are taken into consideration for this practical implementation. Then I keep the keys to be used for the output labels. I keep the key 1 as benign and the key 2 as malignant. Now is the time to do resizing and pre-processing of my images. And all my images may be of different sizes. I want to use the resize operator to reduce it to the standard size, say 224 cross 224. And this is a big process because I have to do this for all the 4000 plus images and it takes time to run this cell and you also have to bear with the same. So once you have completed all these resizing operation for all the 4000 images, can come down and print the images and see. First, I split the images samples into two. One is actually train and other is actually test. And I fix the test size of the image to be 25%, means that 75% I'm going to use it for training and remaining 25% I can use it for testing. So this is how I do by using sklearn.model selection, import train underscore test underscore split. Once I split for a random check, I'm saying like X train of 15, Y train, 15, saying that the 15th image in the training set I have to view. So the 15th image in the training set is a malignant kind of image, and that is depicted here. And if you see this image, you can clearly see the graphs having the axis that is ending up to 224 cross 224. That is evident that we have resized the image to 224 cross 224. Similarly, you can print and see other kinds of images as well. Then I have to normalize my image because I have to do a complex calculation, that too for a large thousands of images. So in order to normalize, I can just divide the individual pixels by 255 because we know that the maximum pixel value is going to be 255. So if I divide each pixel by 255, it will come to the normalized range of 0 to 1. So I used NPRA to globally normalize all the images in the training set by 255. Then I see the shape of the image. The shape of the image is going to be like 861. That is 75% of the total images is 861 coming into training. And 224 cross 224 is the size of every image, height cross width. Then I have three channels, red, blue, green, or hue, saturation, and value. Now from this shape, let us go into the implementation. Means that I have completed all the pre-processing tasks and it is now ready to jump into deep learning pre-trained models, and our first model is going to be VGGNet. So now coming to VGGNet, one of the very good model, visual geometry group network model, which is actually proficient in classifying images at lower rate. Now we are going into the implementation, which is very simply done. Like I'm importing keyrest.layers, and for VGGNet, I particularly require some layers, say dense layer, dropout layer, and flattening layer. So I import all these layers into consideration. The details of what is dense layer, dropout layer, and flattening layer are available in my previous videos, and I request you to watch those for more clarifications. Now coming into TensorFlow.keyrest.models, I want to take the VGG16 model and I want to use pre-process input also because I want to use the pre-trained weights available for VGG16. Now I'm just calling this line. This is the most important line which downloads the VGGNet ImageNet model. So I'm having an object, say VGG16. So I'm just calling VGG16 function with weights equal to ImageNet. Means that I'm taking all the pre-trained weights which is being used to create VGG16 and I use all those and I make trainable as false. Means that I don't want to retrain the model. I want to use the existing weights of VGG so as to use the power of VGG directly. Then I'll apply some transfer learning here, like the entire 16 layers of VGG I'm not going to use directly. So rather what I'm going to use is to transfer VGG to another model which can be usable for my own breast cancer images research. So I just transfer VGG and I name that as transfer VGG16, a transfer model, which takes 18 layers from VGG, include the initialization layers. Then in the final thing, I'm adding some flattening layer, then a dense layer with 512 neurons, another dense layer with 128 neurons. Finally, a softmax output layer with 2 neurons because I have only 2 output labels. So I go with 2. Then I just print the summary of the model so that I can use it in my research articles, like how my summary looks for my ImageNet transfer model. Then I compile the network with Adam optimizer, one of the best optimizers. Then sparse categorical cross entropy for classification task. And I want the training and testing accuracy to be printed. Once the model is ready, where I'm having my transfer model terms being added to my ImageNet, I'm just running the model to fit it into my training data. Here, I want to add you a point, like I have used only one epoch because for want of time, I'm not going for multiple epochs. But I advise you to go up to some 5 to 10 epochs or even more than that based on your own requirements. My requirement here is to just teach you like how this algorithms can be used in datasets. And the basic requirement should be to should accrue higher accuracy like 90, 95 and more than that percentage. But here I'm just using one epoch with itself I'm getting 75% in training accuracy. So I'm just giving one and I want you to increase the number of epochs to more than 5 or more than 10 as well. Then I evaluate the model with the test cases and I get around 79% accuracy. And this is how VGG16 is done. Then going into ResNet, like in ResNet 50 uses similarly in VGGNet 16, like it has some layers like dense, flatten. This also has other layers, say input, 2D, batch normalization layer, activation, additional layers for neuron addition, flattening layer, dense layer, max pooling 2D and average pooling 2D. So I take all these layers into consideration, but on the whole, if you want to remove all, just you can take only one thing like ResNet 101 or ResNet 50. I can name it ResNet 101 because both as actually as efficient as good, but the concept which is being used here matters a lot with good accuracy with ResNet 101. So I go with ResNet 101 implementation. Now I transfer ResNet 101 with 80 layers of the pre-trained ResNet model. Then after the 80 layers, I added some flattening layer. then a dense with 1024 neurons, another dense with 512 neurons, and finally an output layer with softmax activation and two neurons. Hope you all know that why I use two neurons, because I have only two outputs. Then I make the transfer net model very clear, and then go into the summary and compile my model with add and optimizer. And this is what the summary of ResNet 101. Then we will go with the fitting. So once you go for fitting, you'll be getting the accuracy, and finally you can go for evaluation. So it is very simple now. Now you need not change any code in this ResNet model. Just have the p-process layer, run the cells, you'll get the model ready with even more good accuracy than VGGNet 16 for better epochs. Going into MobileNet implementation, I'm adding dense, dropout, and flattening layers. This time I import MobileNet and pre-processing inputs. Similarly, like VGGNet, I call MobileNet, and I make my MobileNet model to be trained with the existing weights. Then I go with the version 2 of MobileNet, and I'm just taking the MobileNet pre-trained models and transferring it to add other models with again a flattening layer, 1024 neurons based dense layer, 512 neuron based dense layer, and finally a 2 neuron output layer with a softmax classifier. So again, a very simple model, especially the thing which is similar to VGGNet and ResNet, no much change in the code, making it everything simple for implementation at ResNet. Then transferring the MobileNet and implementing the training accuracy for one epoch. If you want, you can increase the number of epochs as well. Then this code will be used to test the model to get the testing accuracy. Finally, in the ImageNet version, I go for InceptionNet V3, where we take the similar kind of code. The only change here is make Inception V3 instead of MobileNet. I go with the 3D layers, 224 plus 224 plus 3. Again, going with some additional layers, which is actually similar to using it same as MobileNet models. And here I go with 2056 dense neurons, because InceptionNet V3 is actually a huge model. So directly bringing out the neuron space from a very big thing into 1000 is actually not good. So I go with some 2000. Can go for some other higher number of neurons as well. Then I go with 1028, and finally an output layer with two neurons. You can also go with adding sufficient amount of dense layer or intermediate dropout layers based on your own models or accuracies. And this will add more innovative criterions into your algorithm, especially when you build transfer net models. And as I said before, this code will actually give you the uh, training accuracy, and this will give you the testing accuracy. Now, these are the algorithms which will make you very clear about implementing ImageNet models into a particular data set. But if you see very clear over this, you have not changed any code here. The only thing what I can actually change is to make the drive path alone to be changed based on the location in which my data set for my research or my data set for my practical application is present. And only that drive path will be changed, and none of the other code is being changed. Because we have already seen in our previous videos like how individually each ImageNet models will work in sufficient detail. But this particular video is given especially to ensure that how we can practically implement very easily all ImageNet models and customized models for any standardized image datasets. And that's what we have achieved now. Let us go to some amount of CNN models in customized way. Like I take some sequential model and I just apply a convolution 2D layer with 16 neurons and striding say 3. And with this, I actually go with a ReLU activation and same padding layer, no much different paddings, and going with a max pooling 2D, then again a flattening layer, then going for 128 neurons, and finally a two output classification. If you want, you can increase the number of output layers, you can increase the number of neurons, and so on. The output layer increases nothing but the number of dense layer increases. Going with the number of increased dense layer increases the complexity of the model. So the running time of the model will also increase. And as usual, I said, this code will give you the training accuracy and this will evaluate your model to give you the testing accuracy. Next, we will see another customized deep learning model, CNN model with data augmentation layers and dropout layers, where I give a random network where it starts with a convolution 2D layer, then going with a max pooling layer, then flattening, then a dense layer. Now I have introduced a new layer which we have not seen before called as a dropout layer. Like when I increase the number of neurons in order to make my model somewhat efficient or in order to make it converge at a higher level of accuracy, can use some dropout to activate some neurons which are not working. So in that particular case, I can use a dropout. Here I have used a dropout of 30% of neurons so that my network can perform better than before. And again, I applied a dense and again a dropout and finally an output dense. So I again compile my model and I find the accuracy for this particular new model with augmentation and dropout. I can use a model with only dropout layers more, that is more number of dropout layers also. And this model is actually based on that, like no convolution is there, directly max pooling and going with a flattening layer, dense dropout and a dense layer. So this kind of models can be used when you think that your images are not that much huge and you need not want to lose any features in the images, or if you think that you need not want to compress the images. In that particular cases, you can actually directly skip the convolution and go for max pooling. And finally, it's the CNN model with only augmentation layers, where we use more amount of dense layers so that you augment a lot of features so that your model will learn a lot. But when you increase the number of dense layers, there is a huge possibility that your model will get overfitted. And that is why we use a concept called as dropout so that we don't increase the variance. When you have high variance, the possibility of overfitting will be increased. And hence, we try to lose some features which we actually make the model to memorize. So that particular features will make the model overfit. And hence, using more number of dense layers is not good. And that is what I want to say. Let us go with two different augmentation layers alone. Like going with convolution 2D, max pooling, flatten, dense, and out. A simple augmentation layers. And you can also go for more number of dense layers and so on. If required, we can also go for filters as well, where we can use a batch normalization layer. And this batch normalization layer is nothing but a model which makes your CNN model to run faster in parallel mode, so that if you increase the number of layers also, the model will have some less time for running. So the response time will be good. So this is how you can increase the model and make your model efficient. And the conclusion, what I can actually say is, if you are doing an initial research in deep learning, you can actually take a good standard data set either from a particular standardized website or Kaggle or any other data challenging schemes and download the data set, put it inside either Kaggle Lab or you go to Colab or Google Drive, you put it in the data set inside a particular data source. Then use this particular code, run VGGNet, ResNet, MobileNet, InceptionNet, custom models, aggregate all the algorithms, put all your training accuracies, put the number of epochs it takes to get training accuracy of 100%, put the testing accuracy, say what activation function you used, say what optimization function you used. And that's how and good research goes on in deep learning, especially in the ImageNet criteria. And I hope this particular code will help you understand very clearly and how you actually proceed with deep learning models, especially in the practical scenario, to implement all in one deep learning based ImageNet classification and custom image classification techniques. And that's it. And thank you. And this is Raja Subramanian, Professor.